Alright, thanks for watching, and today I want to show you something really cool, because in a previous video we've shown that if a set in Rk is closed and bounded, then it is compact. And the question is this true in general? And it turns out the answer is no. And in fact, we'll find some weird infinite dimensional space for which even the ball is not compact, which is weird. The ball is so big that it turns out it's not compact anymore. And for this, let's just consider the space of sequences. So let B, not sequences, but let B be the space of bounded sequences. Bounded sequences xn. Okay, and with the following metric, and let me illustrate this with a picture first of all. So suppose this is, let's say you sequence xn, and this is you sequence yn. Then the metric we want to choose is what's sometimes called the infinity metric, which is really the biggest possible spread between the sequences. So if you want the distance between sequences xn and yn, okay, is the supremum of each component. If you want xj and yj, where j equals 1 up to infinity. And that's a metric because the sequences are bounded, and you can show all the three nice properties of metrics that way. And what I'm claiming is, in this case, if you take the ball centered at the 0 sequence and radius 1, this thing is not compact. So claim, if you consider the closed ball, B01, which is the set of all sequences xn, such that the distance between xn and the 0 sequence is less than or equal to 1, I'm claiming that this is closed and bounded. But not compact. So again, it's just a ball centered at the 0 sequence and radius 1. So I'm claiming this closed ball is so big that it is not compact. Alright, now how do you show that this is closed, this is bounded? Well, it is a ball of radius 1, so notice so first of all, bounded. Let's call this f. So press F to pay respects. So first of all, f is bounded, well, because f is included by definition in a ball of some radius r, where r equals 1. Okay, so it is, f is included in the ball, namely the one of radius 1. Okay. So that's not a problem. More interestingly, let's show that f is closed. So let xn, so careful, it's a sequence of sequences. So let's xn, which is xn1, xnj, be a sequence in f converging to x, which is just x1, x2, xj. And we want to show that x is in f. So show x is in f, but that's not too hard, because you see xn is a sequence in f. So since xn is in f, what we know, again, f is the unit ball, of radius 1, we get that the supremum of x and j minus, so 0j, so just 0, where j is from 1 to infinity, it's less than or equal to 1. But the point is, if the biggest possible value of this is less than or equal to 1, we actually get that for all j from 1 to infinity, each value of the sequence, x and j, is less than or equal to 1. And therefore, letting n go to infinity, we actually get that xj is less than or equal to 1. So if you let n goes to infinity, we get that for all j, xj is less than or equal to 1. But then, if you're taking the distance, but then the distance of, if you want x and the 0 sequence, which is just a supremum of xj, where j is from 1 to infinity, because each component is less than or equal to 1, that supremum is also less than or equal to 1. Right? So that is good, and then, therefore, x is an f. That's the whole point. So the distance between x and the 0 sequence is less than or equal to 1. So by definition, x is an f, and therefore we get f is closed. All right. And now, to show that it's not compact, what do we have to show? We have to find one open cover of your space that does not have a finite subcover. And let's consider the following thing. So given x in F, consider u of x, which is simply the ball centered at x and radius 1. So it's just the set of all sequences y, okay, such that the distance between x and y is less than 1. So literally, again, the ball centered at the sequence x and radius 1. And now, let's consider a following counterexample sequence. So for each n, define xn as follows. And define xn simply as follows. So careful, so for each n you have a sequence, so this is a family of sequences, and xn, it's 1 everywhere. Let me just double check, just the correct notation. Yes, so it's 1 everywhere except at the nth slot. So 1, 1, 1, 1, minus 1, 1, dot, dot, dot. So this is at the nth slot. So just picture-wise, what would x1 look like? x1 would be minus 1 at the first slot, and then 1 everywhere else. So this is x1, the first sequence. x2 would be 1, and then minus 1, and then 1, 1, 1, 1, 1. Kind of looks like a square root. And in general, xn would be 1 everywhere, except at n, which is minus 1. So that's the nth slot. Okay, so that's x1, that's x2, and that is xn. All right, very good. Almost like if you know a Kronecker delta function. That's also very similar. All right, I'm claiming, so what do I want to show? So this will help us in our proof. So, but for this, let's now show a little lemma. And once we've proven the lemma, the proof of non-compactness will be easy. So lemma, what I want to show is that distinct values, so distinct sequences xn, cannot be in the same ball centered at x and radius 1. So if m is not equal to n, then xm and xn cannot both be in ux. And that's for any x. Namely, it's almost like marking your territory. So this is x. This is, again, ux, the ball centered at x in radius 1. In each ball, we cannot have two things, xm and xn, at the same time. So once xm is here, there cannot be any other one. In other words, each ball only contains exactly one, or at most one value of this xx. All right, and the proof is not very bad at it's not bad at all. So it's not bad. So it's the proof is good. Okay, so. Because suppose not, that is, m is not equal to n, but xm and xn are in some ux. Then what is going on? Let's look at the distance between xm and xn. Well, both things are very close to x. So let's compare this with the distance of xm and x and the distance between x and xn. Well, xm is in that ball. Remember, ux is the ball centered at x in radius 1. So this distance is less than 1. But also this distance is less than 1. So in fact, the whole distance is less than 2. So distance between xm and xn is less than 2. On the other hand, we want to find a contradiction. We want to show that this distance is equal to. And why is that? Because let's look at xn. So xn, what does it look like? It is 1 everywhere, except at n, it is minus 1. Okay? So this is 1, and this is minus 1 at the nth slot. But then let's look at xm. xm is also 1 everywhere. It's also 1 here, because m is not n. But then it might be minus 1 somewhere else at the nth slot. Then Well, what is the biggest possible distance? Well, here it's 0, 0, 0, 0, 0, 2. And then 0, 0, 0, 0, and then also 2. And then 0, 0, 0, 0. So, in other words, the biggest possible distance between x and xm is actually 2. So, in other words, but d of xm and xn, well, that is the supremum of xmj minus xnj, where j equals 1, etc., which in fact is 2. Or if you like, the distance is at most 2, but it's also greater or equal to xm, if you want, xmn minus xnn, which just becomes, in this case, 1 minus minus 1, okay? And that is just 2. And then we got a contradiction, because on the one hand, the distance is greater or equal to 2, on the other hand, the distance is less than 2, and then we have a problem. So 2 is less than or equal to the distance of xm and xn, which is less than 2. So that's a contradiction, meaning that for every ball, there's at most one of the values of the sequence xn. All right. Now, why? Okay, why did we need the lemma? Because now we can finally attack our proof that f is not compact. And you'll see it just flows like water. Proof that f is not compact. Well, again, what do we have to show? We have to find one cover that does not have a finite subcover. So consider now the following cover. Consider the cover U, which is just all the balls centered at x and radius 1, where x is in your set. So again, this might be F, and then you just cover it with balls of radius 1. With a bunch of ux. Okay. Now, if f were compact, then this would have a finite subcover. So if f is compact, then U has a finite subcover. Subcover, let's call this V, and it sets up the form ux1, ux2, up to, let's say, ux capital M for some centers. So in other words, it's enough really to just cover F with little centers, x1, x2, up to xn, x capital N. So now we just have finitely many balls. All right, and careful, the x1 up to xn, they're not the same as our counterexample sequence. However, now let's use our counterexample sequence. So, what do we know? What about fx1? So consider x1, which is in f. Because you see the biggest possible value of the sequence is, either 1 or minus 1, so definitely less than or equal to 1. But look, since x1 is in F and V covers the whole space, V covers F, there must be some ux, so there must be, let's say, U. U in V with x1 is in U. So basically x1 is in one of those sets. Okay? And well, since it's up to rearrangement, we can just say without loss of generality, assume it's in the first one. So assume that x1 is in the first set ux1. So without loss of generality, assume U is just U of x1, because it has to be U of something. So let's just assume it's the first one. So x1 is in ux1. All right, very good. So x1 is in this one. Well, and now let's consider x2. Consider x2, again in F. Again, since V covers the whole space, we know that x2 is in U for some U in V. Question, can x2 be in the first set? No, it cannot, because remember, we said it cannot happen that two different values of the two different sequences here are in the same set. Remember, we said x1, xm, and xn can never be in the same set ux. So the point is x2 cannot be in ux1. So by lemma, x2 cannot be in ux1 because x1 is already in there. Otherwise, we would have a contradiction. We would find two different xn's that are in the same ux. So, because x2 has to be in one of those sets, but it cannot be in ux1, without loss of generality up to rearrangement, assume x2 is in ux2. x2 is in ux2. All right, and then you can just continue that same way. So we find x2, it's in ux2, x3 will be in ux3, x4 will be in ux4, etc., etc. So basically, we get that at least the first capital N terms are in their respective sets. So continuing, we get, so x1 is in ux1, x2 is in ux2, up to x capital N, which is in ux capital N. All right, and now let's think about it as follows, okay? So we have, again, this is not Hilbert's hotel, but assume you have a hotel with 1,000 rooms, and the first 1,000 guests have been served, but now you have infinitely many guests. What happens to the 1,001st guest? Well, you have to kick that person out, because we said all the rooms are occupied. But then consider xn plus 1. X capital N plus 1. Well, it's in neither of the sets, ux1 up to uxn, which is not in ux1, uxn. But then that's a problem, because then what have we found? We found an element in F that is in neither of those uxi's. But then xn plus 1 is in F, but in none of the uxi's or uxj's. But then that contradicts the fact that V must cover the whole space. Because we know that all the balls here, all the capital N balls, they have to cover the space. But then that's a problem, because we found an element that is not in that cover. So this contradicts V covering all of F. Because by covering, we know this is in F, so it must be in one of those balls. And therefore, what do we get? We conclude that V does not have a finite subcover. Or I guess U does not have a finite subcover. A finite subcover. So we found one, we found one cover that does not have a finite subcover, therefore F is not compact. So press F for not compactness. Therefore, what's interesting, we found a space where the ball is not compact. So it's infinite dimensional space, balls might not be compact, but I believe there's something like the Heine-Borel's theorem, I love that word, in functional analysis that sometimes guarantees that sort of balls are maybe weak star compact or something. But that's not the point of this video. All right, thank you very much.